Hello and good evening. As a recap from our lecture on Monday, I promised that I was going to upload a video on functions, domain, and range. So you recall from our lecture that we started off, in order to be able to define a function, you need to first of all be able to define the Cartesian product. So we define the Cartesian product that given any two sets, given any two sets A and B, you can define the set of all ordered pairs of the elements in the set, so such that A belongs to A and B belongs to B. So in this case, the Cartesian product is a set of ordered pairs of elements in A and B. And we can add all. So you have all ordered pairs under consideration. So if you define a rule in which the elements are ordered, then the resulting subset is what we call a relation. So a relation is a subset of the Cartesian product. So you define a rule that assigns elements of the set A to the set B. So define a rule that assigns elements of the set A to the set B. So you have a certain rule. Notice that for Cartesian product, you're just picking ordered pairs of elements, provided the initial element is from A and the second element is from B. So if you define a specific rule through which you assign the elements in a set, then the resulting subset of the Cartesian product is called a relation. So for example, you could consider, say, in a real life case, let's take, for example, the vending machine. You know, the machine you find at the supermarkets, maybe at the petrol station, at the hospitals, where you just select an item, put in the required amount of money, and the item is dispensed for you. So you find that in the arrangement of the vending machine, you have food items. And the food items will be classified depending on their price. So probably in the upper bar, you'll have items going for 50 shillings. In the second bar, you have items going for 100 shillings. And in the third bar, you have items going for 200 shillings. So you have a rule that assigns the food item a code. So that's an example of a relation. So you have food item and the code. The code in this case would be used to determine the price of the food item. So you have a relation. You have two sets, the set of food items and the codes in this case that are meant to assist you in pricing, knowing the price of the food item. So that's a relation. So you are assigning elements under a certain rule, as opposed to Cartesian product where you just pick and assign them at random. So the relation is a subset of the Cartesian product. Mathematically, I could say, for example, that my set is a set of natural numbers, or maybe I could take my set A to be the set of integers and take my set B to be the set of natural numbers. And with the rule that every integer is assigned to a square. So in this case, so you have a rule. You're not just pairing integers and natural numbers. You're pairing them under this rule. So that if I pick the integer number 1, it will be associated to the natural number 1. If I pick integer 2, it will be associated to natural number 4. Anytime you square a number, you get a positive whole number. A positive integer, you get a positive whole number, and so on. So you have a rule that assigns an integer to a natural number. In that case, the resulting rule is called a relation. So out of relations, and we looked at different properties of relations. I'm not going to repeat that. But out of relations, we have one of the examples of relations which we covered is equivalence relation. Equivalence relations. I gave enough examples, so I'm not going to spend time on this, but it's simply a relation that is reflexive, symmetric, and transitive, where reflexivity means that every element is related to itself. Symmetry means that whenever A is related to B, then B would be related to A, while transitivity now relates three elements: A related to B and B related to C, implies that A is related to C. So a relation that satisfies the three conditions is called an equivalence relation. And he gave examples of equivalence relation, and one that stood out for us was the integers modulo n, and we found that to be an equivalence relation. And we also gave a counter example that when you define the relation divides, so you find that if you define two integers under the divides rule, then it's not an equivalence relation because you find that symmetry fails in that case. So the other example of a relation is functions. So a function is a relation in which every input is assigned to exactly one output. So every input is assigned to exactly one output. In other words, a pre-image has exactly one image. So the vice versa is possible, but a relation in which every input is assigned to exactly one output is called a function. And one of the ways in which we visualize functions is we see functions as an input-output machine. So where you input the element x, you have a rule which you denote by f that assigns our element x to, so you're defining a rule that assigns elements of a set A to a set B, in this case the rule being a function. So a function requires that every output is assigned to exactly one output. So it cannot have more than one images. So exactly one output. So the other way we visualize functions is just the same way we visualize relations. You can use arrow diagrams. So for example, if I have this function a, b, c, and d, x, y, w, z, x, so where every input is assigned to exactly one output. So one of the options is where you have a one-to-one relation. The other option is where you have many to one. So you can have a case where you have say 1, 2, 3, 4. So you have one, A is assigned to A, and it's possible that B would be assigned to 1. So you have the many to one option. So that you can have a case where one output has more than one input, but the vice versa now it fails to be a function. So it's either a many to one relation or a many to one mapping or a one to one or a one to one relation. So, and therefore, when you consider functions, so you have the set of inputs, which we call the domain of the function, and we have the set of outputs, which we call the core domain. So remember, a function is a subset of the Cartesian product. So you have ordered pairs. You can represent it as a relation. So you are looking at ordered pairs x, f of x. Some books, sometimes you write it as xy, where y is f of x. In this case, the inputs being the independent variables and the resulting outputs now depends on the input. So we have the dependent variables. So normally we represent functions as follows. So we have the notation. So function notation. So you write the function, you can use small letters of the alphabet. You have the domain. It's a rule that assigns elements of a set A to a set B. So that's a notation of functions. And when you write a function in this case, the set of all possible inputs, we call it the code outputs, we call it the codomain, and the set of all possible inputs, we call it the domain. And so in some cases, you find that not every element in the codomain will have a corresponding element in the domain. Like in the example that I've just given here, you can see 4 has been left out. So we define the set of all images of a function. So set of all images of f is called the range. It's called the range of f, denoted by R sub f. So we have it as a range of the function. So that by set builder notation, it consists of elements y belonging to B such that y is f of x for some x belonging to A. And we note that the range is a subset of the core domain. So in some cases, it would be a subset properly contained, and when it coincides with the core domain, so that you have when range of f is B, then we say that f is onto or surjective. We mentioned this in a previous lecture. So in that case, we say that the function and the definition is a surjective function. So, and that brings us to the question, how do we find the domain of a function? So how do we find the domain? So normally, under any consideration at our level, the largest possible set of inputs is a set of real numbers. So at this level, we are considering real valued function. So we note that the largest possible set of inputs is a set of real numbers. So the largest possible domain of the function f is a set of real numbers. So in order to find the domain, you start with the larger set, or in interval notation, it's the interval from negative infinity to infinity. So you start with the largest set, but you remove values at which, so remove values that involve division by 0, or finding square roots of negative numbers. Finding square roots of negative real numbers. So in other words, to determine the domain, you start off with the function and remove values at which the function is undefined. And it will be undefined if it involves dividing by 0 or finding square roots of negative real numbers. So we can give an example based on this. So you start with the larger set and then remove points at which the function is undefined. And this would be points that would require that you divide by you divide by 0. So, or find the square root of a negative real number. So, for example, take f of x to be the square root of 3x minus 5. So, can we find the domain? So, you start with the larger set. Take R and ask yourself, at which values do we have that the function would be undefined? Our function is a square root function. So we'll have a case where the function is undefined if it will require us to find the square root of a negative real number. So the condition should be that the domain would be the set of real numbers such that 3x minus 5 is not less than or equal to 0, or is not less than 0. So in other words, we say points at which 3x minus 5 is greater or equal to 0. Otherwise, if it's less than or equal to 0, then the function fails to be undefined. And so from elementary mathematics, we can solve for x. So in this case, you'd be looking at values that are greater than, so if that are greater than 5 divided by 3. So x greater or equal to 5 divided by 3. And you can write it even in interval notation. So from 5 over 3 to positive infinity. So that would be the domain of the function. So simply looking at values at which the function is undefined. So if I'm to give a second example, say for example you have a good example, maybe you have f of x being the function x squared minus 7x plus 10 divided by x squared plus x minus 6. So our function would be defined points at which the divisor is not equal to 0. But it's also important for us to look at the upper part. So in this problem, the first thing that you need to do is to just look at the denominator. So you're looking at values where x squared plus x minus 6 is not equal to 0, meaning that you omit values of x such that x squared plus 6 plus x minus 6 is 0. And that would mean solving a quadratic equation, which everyone can do. So use the product difference rule, product sum rule. So minus 2x minus 6 equal to 0. So x into x plus 3 minus 2 into x plus 3. So this gives us x plus 3 into x minus 2 equal to 0. So meaning that for this problem, you're removing x cannot be equal to, for it now to be defined, x should not be equal to negative 3 and x should not be equal to 2. Otherwise, if it's equal to negative 3, you get a 0 in the denominator. If it's equal to 2, you still get a 0 in the denominator. So you have the range of the function. You'll take the set of real numbers, remove negative 3, and also remove 2. So this would be negative infinity to negative 3 union negative 3 to 2 union 2 to positive infinity. So you are removing these points in the interval. So you only consider the points, the blue points, remove 3, consider this interval in between, and after you removed 2. So we have this as the domain of the function. So to find the domain of the function, you simply need to remove points at which you'll be required to divide by 0 or to find the square root of a negative real number. So, and that's how we find the domain of a function. And so how do we find the range? So the range will be determined by inspection. from the values you've gotten, inspection of the domain, because our range is determined by the domain. So once you've determined the domain, then it's easier for us to tell all the possible values of f. So for example, if I take the first function, f of x equal to root 3x minus 5. So we always know that for the square root to qualify as a function, we only consider the positive value of the square root. And so at any one time, f of x will be a value greater or equal to 0. So this is the possible largest range for this particular function. But you're restricting to x equal to 5 over 3. And you can see when you take x equal to 5 over 3, that's a 0. So at any time, it will be a value greater or equal to 0 because you're looking for values that will give you a positive value under the root. And so we can say that the range of the function in this case is the interval 0 to positive infinity, or simply write it in set notation. So it consists of values that are greater or equal to 0. So once you determine the domain of a function, then it should be easier for you to determine the range of the function. So we looked at examples of functions, and these will be repeated again in your calculus. But one of the functions we looked at, we defined composite relations. So as a result, can we also define composite functions? Yes, we can, where composite function is simply a combination of functions. So you have two functions and you have another function b to c. We can combine these two functions, but you need to check what is the codomain of the initial function and what is the domain of the final function. So they must be the same, otherwise you'll not be able to combine the functions. So if I'm to use the arrow diagram representation of functions, so combination of functions or composite functions work as follows. So you have an original element, then you have the pre-images. So you allow f to act, so that at this point y is f of x. So that when g acts, g is acting on y. And it's the same as getting g f of x. So the resulting element in the set is g f of x. And so the combined functions allow us now to move to define a relation from A to C. And you can see the relation here takes x to g f of x. So this relation is what we call the composite function. So called the composite function, and denoted by G composite f, which is G f of x. Notice that when you define composite functions, you start from the right. So you're starting with f followed by G. Let me give an example of a composite function where we determine the composite function. Say, for example, you're given f of x is 2x plus 1, and you're given g of x is 3x squared. Can we find f composite g? Can you find g composite f? So, and in this case, the domain, we notice that they are both real valued functions, no restrictions. So we can combine in whichever direction. So that f composite g by definition would be f of g of x, meaning that where there is an x in f of x, you put in g of x. So this would be the same as 2 into 3x squared plus 1. How about g composite f? By definition, this is g f of x. And so where there is an x in g, you put in f of x. So this would be 3x, 2x plus 1 squared. So we can find composite functions, or it's possible for us to combine two functions. So as I wind up, we have another example of function, very important, that we work with, the inverse of a function. Simply a relation that takes you back. If f is from A to B, then the inverse takes you back from B to C. So the rule in the forward direction, is it possible to find the inverse? The only way we can be able to define the inverse on condition that f is 1 to 1. Otherwise, if it's many to 1, it's not going to be possible, because you'll be left wondering, which one am I taking back? For example, if it's many to 1, it means there's some elements have been assigned to the same image. So if you're taking back the image, then you end up with two elements. So let me explain this. For example, if I have, let's go back to a vending machine. So let's use the example of a vending machine. So in a vending machine, you have the food items. I have the food items in the first row, in the second row. Maybe these ones I've assigned them code 1. So all the items here have code 1. There could be different items. Provided each cost 50 shillings, then it's assigned code 1. The other items that cost 200 shillings, we call them item 2. The other food items that cost 200 shillings, we call them item 3. So every food item has a code. So if my relation is food item to a code, then it would be as follows. I have my food items here, A, B, C, D, E, F, G, whatever, so many. But I have only 3 codes, 1, 2, 3. So I can have item A is assigned to code 1, item B is assigned to code 1, item C is assigned to code 3, item D, each one of them must have a code. And so you find that since every item has been assigned to a code, exactly one. So you notice that a food item has exactly one code. Then this is a function. And it is an example of a many-to-one function. So the relation is a function. However, if I define the relation as code food item, look at what happens. If I assign it code food item, I have my codes here, and I have my so many food items here, A, B, C, D, E, F. So you can see one is assigned to A, one is also assigned to B. You see already the condition for a function fails because you have an input assigned to more than one output. So this fails now, not a function. But if you look at this example, if I'm to define, for example, the first case, if I'm to define a rule that takes me back, taking me back means I'm here. And so the inverse doesn't exist because it's not in, the inverse doesn't exist because it fails to be a function. So this is the forward direction and this is the inverse. My relation initially was food item code. And now I want to go back, code food item. So if I define code food item, then it fails to be a function. So a many-to-one kind of relation is not invertible. So the inverse does not exist. So the only conditions under which a function will be invertible is if it is 1 to 1. That way you're able to take the function. Every element is uniquely assigned to a value. A good example mathematically would be if I'm finding, say for example, the square f of x equal to x squared. So, and it's a real valued function. This is not invertible because if, for example, I'm taking the number 2, the number 2 goes to 4, the number -2 again goes to 4. So if I'm to revert, then I'll have 4 having more than one output. You know, if I were to look at the reverse, so it's not one to one. It's not one to one. And in general, one to one for functions will mean, in general, f of x1 equal to f of x2 implies that x1 must be equal to x2. So this is the definition of one to one. That if they have the same image, then the two elements must be the same, meaning that every input is assigned to an output, to exactly one output, and you have a bit of uniqueness. So every input has its own output. So in that case, the function is said to be one to one. So the only time we can determine the inverse of a function is if the function is one to one. So assuming that our function is one to one, we can always define the inverse, a relation that takes you back. For example, take f of x equal to, say, 2x plus 4. There's uniqueness here. So at any time, you'll have unique values for each value. Each value x has a corresponding unique value f of x. And so we can invert the function. So how do we find inverses? So how do we find f inverse if it exists? So you find f inverse by making x a subject. So for example, here you have y is 2x plus 1. So when you make x a subject, x would be y minus 4 divided by 2, meaning that f inverse of y is a function y minus 4 divided by 2. So if you want to revert to the original expression of a function, you can substitute x because x is a dummy. So simply means taking back. And in general, we have that we take y to be f of x, apply the inverse on both sides. This would be f inverse of y equal to x. And we get an expression for f inverse. But you have to take back. So when you're talking about inverse, it's like these two variables are interchanging roles. So initially, y is the dependent variable, x is the independent variable. When you apply the inverse, you now start with the inputs. The outputs become inputs. And so our outputs y now for the inverse are the independent variables, and the resulting dependent variable is x. But for uniformity, you can always revert back to the original variable, f inverse of x. And so that is how we find we define functions. We find the domain and the range of a function. So kindly practice and read more on functions, domain and range. And also, I'm sure you are going to encounter functions, domain and range again in your calculus. So my advice would be that you take time and practice and understand the concept of finding domain ranges and inverses of function. Otherwise, thank you very much, and I wish you all the best.